Alright, so welcome to our review of sequences for Math 1. And before we get started, I just want to review a little bit of vocabulary to make sure we're clear on some of the words that we're going to be using throughout these videos and throughout the next several questions. First of all, a sequence. What's a sequence? A sequence is just an ordered list of numbers. And so what we mean by an ordered list of numbers, basically we just mean, when we say ordered, we just mean there is a pattern, right? So they're not just random numbers, but there's actually a pattern to the numbers. So for instance, if I said 2, 5, 8, 11, 14, there's a pattern to these numbers. They're not random, right? So what's the pattern? Well, it looks like what's happening each time is that we're adding 3. So if a pattern is adding by the same thing each time, then we call that arithmetic. So that's just a word that describes what type of pattern it is. So in this case, an arithmetic sequence. So arithmetic, meaning that we're adding the same thing each time. And sequence, meaning that there's a pattern. So, what is it not? So for instance, 1, 3, -7. So these numbers are all random, right? So it's just a random list of numbers. So if it's random, it's not a sequence. Now, you might say, well, what about this? That's not random. True, it's not random, but what's happening is that we're not adding by the same thing each time, because that would be +2, that would be +4, +8. So that's there's a pattern, which is a different type of pattern, right? And so that has a name. So a type of pattern that changes because you're multiplying by the same thing, we call that a geometric sequence. So it's still a sequence because it's ordered. It has a pattern. It's just the pattern's a little bit different, right? So the pattern on this case is that it changes by multiplying by the same number each time. So times 2, and so on. So again, it's not random, right? This is not a sequence, right? Because it's random, so it's not a sequence. And then something like this is a sequence, but it's not geometric, right? In this case, because you're adding by the same thing. So notice the difference too, and this is, I think, a nice visual. If you notice what happens here with something that's arithmetic, it's almost like a staircase, like it's going up by the same amount each time, right? Whereas if you look at something that is geometric, you'll notice that it starts off small, and then there's a bigger jump, right, than the one that was previous to it. So what we're going to end up kind of coming to discover is that something that's arithmetic has this kind of constant rate of change, whereas something that is geometric has this kind of increasing rate of change. Alright, so now that we kind of laid out some vocabulary, let's see what that would look like in the context of a problem. Alright, so they give us some boxes, D, so that's days. I don't know, maybe we work at a box factory, and so we're making boxes. And so on day 1, we've got 3 boxes. Day 2, it looks like we've got 1, 2, 3, 4, 5 boxes. So all I'm going to do, first of all, is just make a table. We're just trying to organize the information. So let's say days, and then, so we'll say, I don't know, boxes. So on day 1, by the way, I'm going to skip a little space here, and we'll see why in a second. So leave a little space right there. So day 1, there's 1, 2, 3 boxes. Day 2, 1, 2, 3, 4, 5. And then day 3, 1, 2, 3, 4, 5, 6, 7. And if we haven't already seen the pattern, hopefully we do now. 1, 2, 3, 4, 5, 6, 7, 8, 9. So it looks like what's happening each time is that each day we have 2 more boxes. So +2, +2. So we know that this is because we're adding by the same thing each time. We know that this is going to be an arithmetic sequence. So we know this is going to be arithmetic because we're adding. And so what we want to do is that we said a moment ago that something that is arithmetic has this kind of constant rate of change. Well, and so in this case we have that. So if I were to graph that, just to get a view of what that would look like on a graph, so let's say days, so we could say days and we could say boxes. So we've got 1, 2, 3, 4 days, and we've got 2, 3, 4, 5, 6, 7, 8, 9. So one day we've got 3 boxes, and 2 days we've got, let's use a different color here. So let's say 1, 2, 3, 4. So 2 days we've got 5 boxes, 3 days we've got 7 boxes, 4 days we've got 9. So we see this what we would call is a linear relationship, right? Because this makes a straight line. Right? Now we're actually not going to connect those dots, because what we're saying is that could we have 2.5789 boxes, right? Could we have a decimal? So we would say that these are discrete values. That they can only take on certain values, and in this case, whole numbers. So we're actually just going to leave that as those points. All right. So that's the pattern. It's basically just adding 2 each time. And so what we try to do is that we, if you've heard me before, I talk about a thing called Mathlish and English. The difference there is that if I could write something in Mathlish, or I could write something in English. What do I mean by that? Well, what I mean by that is that if I could write 2 plus 2 equals 4. I could write that out into words. But as much as you may not believe this, within math we actually try to do less work, not more work, and we try to look for ways to simplify things and write things in a more succinct, which means a kind of simpler, write it in a way that's less involved or less work. So I could write all of that, right? 2 plus 2 equals 4, or I could write 2 plus 2 equals 4. So I said the same thing, I'm just saying it without using words, right? This uses words, this uses numbers. So what I could do is that I could say, okay, hey, there's a sequence, it goes up by 2 each time, but those are all a bunch of words, right? So what I want to figure out is that what's a way that I could write this to where I'm only using basically just numbers and symbols, right? So I'm not using words. So, well, let's figure out what that would be. By the way, there's one other thing that we should mention here real quickly. I told you to leave a space. And I left that space because we want to know how many boxes did we have at day 0, right? So if you think about a stopwatch, where does a stopwatch start? Does a stopwatch start at 1? No, if we think about a stopwatch starts at 0. Like how we mark time is we start at 0 and then we say go, right? And then the stopwatch goes from there. But the stopwatch always starts at 0. So when we identify a starting point in a problem, we want our stopwatch to start at 0. So what they did in this problem is that they told us, oh, well, this is what it was after a day. Well, but we want our stopwatch to start at day 0. So, well, let's kind of work backwards then. If we had 3 boxes after 1 day, what must have we had on day 0? Well, if it's plus 2 every time, so if we work backwards, then what plus 2 would give me 3? Well, this would have to be a 1. So it must have been that on day 0, right, when we started the stopwatch, that we had 1 box. And this is an important idea because, again, when we think about counting and where do you start with counting, we start with this idea of the stopwatch where we start at 0 and then we count from there. So the difference is that maybe when they give us the problem, maybe they're not starting at 0. Maybe they tell us, oh, this is what's happened after 2 or what's happened after 3. But what we want to do is we want to start at 0. So it must have been that there was 1 box on day 0. So now the Mathlish to English part. So in English, what I could say is that the recursive, by the way, the two things here, recursive and explicit. Think of the recursive is basically just saying how it changes. So if I said how it changes, well, how does this thing change? Well, it adds 2. So you take the one before it, right? Like if I wanted to get to 9, I take the one before it and add 2. Or if I wanted to get to this one, you take the one before it and then add 2. So you take the one before and add 2. Take the one before and add 2. Okay, so that's what we would say in English. And so what we would say in Mathlish is, okay, take the one before it. So the number that you want, and we'll call that f of n. You take the one before it. Well, the one before n, we'll say n minus 1 to mean that that's the one before it. And then however it's changing. So in this case, it's changing by adding 2. So let's make sure we understand what this is. Right, so this tells you, so this is the one you want. So the term, or the, think about it as the number you want. So the number you want. So to get the number you want, you take the one before it, and then you're going to add 2, right? So if I wanted to know, for instance, if I wanted to know what it was on day 4, I would take the one before it, and I would add 2, which would give me 9, right? So all this is just a shorthand notation instead of writing all this stuff out into words. So my recursive would be the one you want is the one before it, right? So the n minus 1 just means the one before. And then what are we doing each time? Well, we're adding 2. Now, the problem is that, so what if I wanted to know, what about day, I don't know, day 100? Well, I don't know that I want to keep doing plus 2, plus 2, plus 2, plus 2 forever, right? It's too much work. So what I then want to know is that, okay, well, what would be a shortcut? So that's what the explicit is. The explicit gives us the shortcut. See, the recursive doesn't really give us a shortcut. It just basically says how it's changing. The explicit actually gives us the shortcut. So what we do is that with the explicit, so this was our recursive. So with our, in English, what we're doing is we'll take where it starts, plus how it's changing. Okay, so where does it start? So we're gonna take the number we want, and we're gonna take where it starts, and so we'll say where it starts, which is, you know, where the stopwatch starts. So in this case, the stopwatch starts at 1. So we're gonna say 1. And then what we're going to say with that is, okay, well, it starts at 1 plus, how is it changing each time? Well, it looks like it's being multiplied by 2. Right? So in this case, we'll say multiplied by 2. And then how many times are you multiplying by 2? Well, it depends upon how many times you want to know, right? And what I mean by that is that, like, if I were to rewrite my table, let me take another view at my table. So we're starting at 1, and then what we're doing each time is that for each day that goes by, we're adding 2 more than the day before it. So a day 2, I'm starting at 1. And then I'm going to add 2, and then 2 more. And then for day 3, right, I'm starting with 1, and then I'm saying 2 more plus 2 more plus 2 more, right? Because that's what's happening each time, is that you're adding 2 more onto 1, right? Adding 2 more onto 1, adding 2 more onto 1, and then that pattern just keeps going on and on forever, right? So as a shortcut, instead of saying plus 2 plus 2 plus 2, right, couldn't I just say times, right? Because multiplication is a shortcut for addition, right? Because that would give me 3, 5, and then 7. So couldn't I just say 2, if I wanted to know how many boxes would there on be day 3, couldn't I just say 2 times 3, right, the number of days, so 2 times 3 is 6, plus the one you started with, and that gives you 7. So for instance, if I wanted to know how many boxes would there be on day 100, I kind of ran out of a little room here, but wouldn't 100 just be 2 plus 2 plus 2 100 times, right? So couldn't I just say 2 times 100 plus the one that I started with, which would give me 201. So it's a shortcut. So instead of me having to keep doing plus 2 forever, I just noticed the pattern is that it's the number of days times 2 plus the one box you started with. So what we're going to use then is that as a variable, we'll say 2n. And you can check to see if that works. Plug it in. On the 4th day, I have 9 boxes. So 4th day, 9 boxes. So 2 times 4 is 8. 8 plus 1 is 9. Okay, that works. 3rd day, there were 7 boxes. 2 times 3 is 6. 6 plus 1 is 7. So it checks out. So it's the explicit is a shortcut that lets me know how to find any one. So what we ended up doing here is we ended up saying 2 times n. So it starts at 1 plus 2 times whatever it is you want to know. All right, so the first 2 are going to be kind of the longest problems of all of the things on here because we're kind of laying the foundation, and then I think you'll see it'll go pretty quickly from here. All right, so go ahead and try number 1 on the right side. Come up with the table, the graph, the recursive, which is basically just how it's changing, and then the explicit. The recursive, by the way, always starts the same. Every recursive starts with f of n equals f of n minus 1, and then just however it's changing. I should also mention, too, at this point real quick before we close out this video, is that there are different notations that you might see with this. So as an alternative, this is kind of written in more of a function notation. Just know that you may have seen f of x equals f of x minus 1 plus 2. That means the same thing. Or if you may have seen a sequence notation that looks like this, a sub n equals a sub n minus 1 plus 2. So there's a couple different notations, but they mean all the same thing. Because in our workbook for this unit, the workbook used this particular notation, I will be using that notation for this for these videos, but just know that it all means the same thing. All right, so go ahead and stop here and try number 1 on the right side.